Hey guys, welcome back to another lecture video for Chem 115. In previous lecture videos, we discussed what integrated rate laws are and how to apply them in a word problem setting. Now, in this lecture video, we will move to the next topic in this chapter, which is called collision theory. Now, when you guys were studying first semester of general chemistry, specifically when you guys were learning how to balance chemical reactions and using them in stoichiometry problems, you may have developed an idea that if you put two reactant particles together, and in this example it's going to be nitrogen gas and oxygen gas, that's currently present in our atmosphere. A reaction can take place that will automatically give rise to product. And the product in this example is going to be nitrogen monoxide. And so if we kind of magnify that logic, that whenever a nitrogen gas collides with an oxygen gas, it'll automatically produce the product, one can assume that we will have a large concentration of nitrogen monoxide present in our atmosphere. However, the reality is that we have a higher concentration, higher amount of nitrogen gas and oxygen gas than this specific product that's in our atmosphere. And so overall, this is telling us that there are other factors that's dictating whether or not a product can be formed from the collision of two or more reactants. And so collision theory is going to attempt to describe these factors that dictates whether or not a product will be formed. And so according to collision theory, the rate of a chemical reaction is proportional to the number of effective collisions among reactant particles or reactant molecules. And an effective collision can be quickly described as a collision that gives rise to product. And so it turns out that there are three factors that lends to the effectiveness of a collision. And so the first part to the collision theory is that particles must collide. And so if you have these reactant particles and they're far apart from each other, then one can assume that no reaction will occur. For a product to be formed, those reactant particles must collide. They must make contact with each other. Another part to collision theory is when these reactant particles collide, the orientation of the molecules does actually matter. And so if the orientation of the molecules are not aligned in such a way that will give rise to product, then those molecules will simply bounce away and still retain their current identity. Last but not least, according to collision theory, when these reactant particles collide, they must have enough kinetic energy to overcome what's known as an activation barrier, or commonly known as activation energy, which is capital E, abbreviated as capital E subscript A. And so we're going to go ahead and discuss these three parts of the collision theory in greater detail. And so the first item that we're going to discuss is the collision of these particles and how that will affect the rate of reaction. And so we know that if particles do not collide, then there's a high chance that the products will not be formed. And so the frequency of collisions, the rate of the reaction, is proportional to the frequency of collisions. And the frequency of collisions is reflective of the amount or the concentration of reactant particles that's present in solution. And so, for example, if we're taking a look at this diagram, if you have a low concentration or a low amount of reactant particles, one can assume that there's a lot of empty space in between, and therefore there's fewer collisions that can occur. And if you have fewer collisions occurring, then you have a lower probability that these reactant particles will be converted into product. Now, when you're comparing this to a solution that has high concentration or high amounts of reactant particles, per given the same space as this example, more collisions will most likely be observed when there's a high amount or high concentration of reactant particles. And so one can assume that if there are more collisions occurring due to the high abundance of reactant particles, then you have an increased probability for the reactants to be converted into products. And therefore, the rate of the reaction is going to increase compared to low concentration reactant particles. All right, so the next part of the collision theory that I want to discuss is the orientation. And so let's just say that you want to form carbon dioxide. And so if you guys are looking at the Lewis structure for carbon dioxide, it's very specific. We have a central carbon, and surrounding this central carbon are two oxygens. And so if you wanted to form carbon dioxide from, for example, carbon monoxide and oxygen gas, when these two reactant particles collide, it is more likely that a product could be easily formed if the carbon atom faces directly to one of the oxygens of this diatomic molecule, compared to this scenario where this oxygen is in line or making contact with another oxygen from this oxygen molecule. And so the idea is that when these reactant particles collide, it should be oriented in such a way that it's primed to automatically produce the product in the correct geometrical form. And so, in short, the frequency of collisions can dictate the rate of the reaction, and the molecular orientation of the reactant particles when they collide can also influence the rate of the chemical reaction. If these reactant particles are well aligned, such that the transition state looks very similar to the product, then it's more likely that the product can be formed versus a transition state that doesn't look like our product. And so I mentioned the transition state a little too early. I'll go ahead and explain transition state in a few slides down. All right, so the last item that I want to talk about with respect to collision theory is this idea of sufficient energy, or having enough kinetic energy to overcome this activation barrier. And so it turns out that molecular collisions are only successful when they have enough kinetic energy to break bonds that it currently has, and has enough energy to form new bonds. And so this minimum amount of energy that's required for the reaction to actually occur is known as the activation energy, which is abbreviated as capital E with a subscript A. And so overall, one can imagine that the energy of the collision must be greater than the activation energy for a product to be formed. And so in general, the larger the activation energy, the slower the rate of the reaction. And so the converse also is held true. If the activation energy is small, then the rate of the chemical reaction is going to be much higher. And so one can imagine that if you have a large activation energy, you'll have a smaller fraction of molecular collisions that will have the sufficient energy to form product. Whereas if you have a lower amount of activation energy, if you have a small activation energy, you'll have a higher fraction of molecular collisions that has sufficient energy to form the products. And so if you have, for example, a large activation energy, and if you wanted to increase the rate of the reaction, one way that you can do that is by changing the temperature. And so it turns out that temperature plays a strong role in the energy of the molecular collisions. And so if you guys increase the temperature of the environment, that's going to increase the kinetic energy that those molecules will have. And if you increase the kinetic energy, then the frequency of collisions is going to increase, and therefore you'll have a higher probability that those molecules will be able to sample the correct molecular orientation, and it will have a higher amount of energy required to overcome the activation barrier or the activation energy. And so by increasing the temperature, and I've kind of typed it out over here already, if you increase the temperature, the kinetic energy of the particles is going to be much larger, and therefore their speed is going to be greater, and therefore the force of the collisions will be greater, and the frequency of collisions will be higher. And so overall, you will have a higher fraction of collisions with a collision energy that's much, much greater than the activation energy, which in short will enable the reactants to be converted into products. And so we would term that as an effective collision. And so we can go ahead and demonstrate the effective temperature by looking at this Gaussian curve, where the y-axis represents the number of molecules that has a specific amount of energy. And so as we go from left to right, the amount of energy increases. And so looking at this orange line, well, let's go ahead and take a look at this purple line. So this purple line is representing the range of kinetic energy that's available to this population of reactant molecules at higher temperatures. While this orange line is representing the range of kinetic energy, or the range of the energy that's available for these molecules at a lower temperature. And so let's just say that the activation energy is somewhere around this point, as seen by the blue line. And so if we're using this blue line as a reference point for activation energy, any molecules with an energy that's less than the activation energy, and on this graph it's going to be represented as the area to the left of that blue line, these are molecules that do not have enough kinetic energy to overcome the activation barrier and therefore will not produce any product. And so any molecules that is underneath the curve, the area underneath the curve, will have an activation or will have a kinetic energy that's much larger than the activation energy. And therefore, these molecules is most likely to form product if they actually collide and if the molecular orientation is correct. And so looking at specifically the area under the orange line, the area under the curve that's marked by the orange line, you have all of these molecules that will not have a sufficient kinetic energy to overcome the activation energy, and therefore will not produce any product. And so you'll only have a small fraction of molecules that will have enough kinetic energy to overcome the barrier. Now, if you increase the temperature, if you go from a lower temperature to high temperature, what you're doing is you're shifting the Gaussian curve to the right, such that you will have a larger fraction of molecules that will have enough kinetic energy for it to overcome this activation barrier. And so if you have a higher proportion of molecules that have that can surpass or overcome this activation energy, then you will have more reactants being converted to products, and therefore the rate of the chemical reaction will increase. And so this is the reason why when we increase the temperature from lower to higher, we typically see an increase in chemical reactions, or in rate of chemical reactions. And so what I want to do next is I want to take this Gaussian curve and kind of depict in a different way. So what I want to do is I want to create a reaction profile. And so I do encourage you guys to take a look at this YouTube link that I posted, and you guys are going to start at 30 seconds. And so this YouTube video will give you a visual of how these reaction profiles are created. And so these reaction profiles, another name for them is a potential energy diagram. And so a potential energy diagram tracks how changes in energy is occurring as the reaction progresses. And so what we're doing is that we are comparing energy against the progress of the reaction. Whereas in this diagram, it's comparing the fraction of molecules, or the number of molecules that have a specific amount of energy. So we're profiling the reaction in a different way, such that we're comparing changes in energy against the progress of the reaction. And so the transition typically goes from reactant to this idea of transition state, and finally into products. And so transition states is this hybrid structure that has parts of it that looks like the reactant and parts of it that looks like the product. And so we'll go ahead and take a look at an example of what a transition state looks like in just a little bit. But first, I want to show you what a reaction profile or a potential energy diagram looks like. And so this is an example of a potential energy diagram such that the energy of the system, specifically the potential energy, is found on the y-axis. And on the x-axis, it's going to represent the progress of the reaction from reactants to products. And so the idea of potential energy comes from the energy that's stored in the bonds of these chemical compounds. So for example, if you guys have carbon dioxide, the potential energy that's stored in these bonds over here, it's going to have a fixed amount. And so therefore, the energy of the reactants is going to have a fixed amount. And it's an arbitrary amount. It does not start at 0. Okay? It typically has a value above 0. And so this potential energy diagram describes that as the reaction progresses, at some point the potential energy increases until it gets to the top of this hill, so to speak. And then it's going to go back down to reflect the potential energy of the products. And so before I get into the details of the potential energy diagram, I want to go ahead and take a look at this idea of transition state. And so typically a transition state is marked by this symbol. Another way that you guys can write the symbol is a vertical line, one vertical line, and two horizontal lines. And so this is going to represent the symbol for transition state. So when you guys are looking at a chemical reaction, in other words, a conversion of reactants to products, the transition state, also known as the activated complex, has parts of it that looks like the reactants, right? So this piece and this piece, if we kind of put them in, segregate them in little boxes, looks like the reactants. And parts of it is going to look like the products. And so here I boxed that off, and I'm going to go ahead and box this part off. And so this activated complex is known as a transition state, is a hybrid structure between reactants to products. And this dotted line represents the potential of bonds being formed or broken. And so what do I mean by that? Well, if this transition state typically represents the top of this hill, then if this bond was not formed and this bond is formed, then it'll look like our reactants. In other words, on a potential energy diagram, we're going from the transition state back to the reactants. And so that would be a scenario in which, for example, when two reactant molecules collide, they don't have the sufficient kinetic energy to overcome this activation barrier. And so in other words, it will not have enough kinetic energy for this bond to be broken and this bond to be formed. And so if the reaction progresses in the forward direction such that the products are formed, then that means that this bond will be formed and this bond will be broken. And so that allows this molecule to look like the product that's observed here. Okay, and so the main point that I'm trying to get at is that the transition state is a hybrid structure to reflect both reactants and products. And these dotted lines are potential bonds that could be formed or broken, depending on whether or not the reaction actually pulls through to the right or if it will stay as reactants. And so this is another image of a potential energy diagram that's a little bit different than what I showed you up here. And so what these two reactants is actually depicting is nitrogen monoxide and chlorine gas. And so here, as nitrogen monoxide collides with chlorine gas, its potential energy is going to increase until it reaches the transition state, which is essentially this complex. And so if the reaction does pull through to the right, meaning that NOCl is formed and Cl is left alone, then the products will finally be made. All right, so now that we have taken a good look at what these potential energy diagrams look like, let's go ahead and kind of go through the details of potential energy diagrams. And we're going to go ahead and look at potential energy diagrams for both exothermic and endothermic reactions. And we're going to look at characteristics that differentiates them between the two. And so the first thing that I want to put on this empty potential energy diagram is reactants and products. So I'm just simply labeling my reactants and I'm labeling my products. And so the y-axis represents potential energy, and the x-axis represents the progress of the reaction. So there's another item that I want to do. I want to create dotted lines. And these dotted lines are just extrapolations at specific points on the potential energy diagram. And so I'm going to go ahead and kind of extrapolate this line right here. I'm going to put a whole bunch of dotted lines. And then I'm going to go ahead and do the same for the products. And last but not least, I'm going to go ahead and do the same for the peak of that hill. Okay. All right. And so at the peak of this hill is going to be the transition state. And so I can go ahead and represent the structure of this transition state as reactant A with ... to reactant B. So it's this hybrid structure, if you will. All right. So now that we kind of understand the parts and have created these dotted lines, let's go ahead and go through the details. And so as reactants are colliding, their potential energy is going to increase. So this section of, let me see if I can do, I'll just highlight it. So this section of the potential energy diagram can be seen as the investment of energy. And so this investment of energy allows, bonds to kind of break and all of that stuff, or subtly break until it reaches this transition state. So anything past that hill is going to be a return of energy. Return of energy. So you guys can think about this as like a monetary system. If you're an investor, you're going to invest, I don't know, $1 million into a company. And so that investment of the energy can also be termed as the activation energy. And so the activation energy starts from the energy of the reactants. And this is the reason why I drew dotted lines. So it's going to start at the energy of the reactants, potential energy of the reactants, and it's going to go all the way up to the top of this hill. So this is known as the activation energy. And so since we're starting from reactants going forward, we're going to say that this is the activation energy for the forward reaction. And we can quantify this by looking at the numbers on the side. And so if the potential energy at the peak of this hill is 100, and if we're starting at 40, then the activation energy for the forward reaction is going to be 60 kilojoules. And so once the reaction passes the transition state and it goes down this hill, it's returning energy. And so this is where your business is getting some profit. Now, when the return of energy equals to the amount of energy invested, this is going to be known as your 0 point. I like to call it as the 0 point. And so, once again, this idea of a 0 point is the amount of energy invested is equal to the amount of energy returned. And so notice that for this potential energy diagram, the line continues further down. And so this is telling us that there is going to be an excess amount of energy that's being produced as reactants is being converted into products. And this excess energy, which is basically the difference of this dotted line at the 0 point, all the way to the potential energy of the products, is known as enthalpy. And so enthalpy, or change in enthalpy, is going to be delta H. And so notice how the line goes below the 0 point, right? So this is the 0 point right here. And so since this line goes further down below the 0 point, then that's going to give a negative value to enthalpy. And so this is going to be negative delta H. And if you guys recall from first semester of general chemistry, if you have negative delta H, then this is describing an exothermic reaction, such that the excess energy that's produced is given off as heat to the surrounding. Okay. And so let's just say that your chemical reaction is starting a fire. So you have a campfire. And so if you are standing around the fire, you are part of the surrounding. And the chemical reaction, the combustion reaction, is like the focal point. And so that reaction is going to give off heat in which you can feel. And so you would say that the combustion of these logs that are caught on fire is an exothermic process. And so this potential energy diagram that you guys are seeing does reflect a potential energy diagram for exothermic reactions. And once again, it's because the change in potential energy goes far lower than the 0 point. And so overall, you can observe that the potential energy of the reactants is much greater than the potential energy of the products. So that's one way that we can classify exothermic reactions through the perspective of potential energy diagrams. And I abbreviate potential energy as PE. KE is going to be kinetic energy. And so the potential energy of the reactants is going to be greater than the potential energy of the products. And so therefore the difference between the two potential energy of the reactants and products is going to be given off as heat, okay, in which delta H is negative. Another way that you can characterize exothermic reactions is based on activation energy. And so looking at what I wrote down over here, this uphill or this increase to the top part of this potential energy diagram is reflecting the activation energy in the forward direction, and that's 60 kilojoules. And so this potential energy diagram can also be seen in reverse, such that if our starting point is the products, and if we're going back to reactants, there's also an activation energy that's involved. And so that activation energy is marked from the potential energy of the products all the way up to the top part of this diagram. And so this is the reason why I was creating these dotted lines. I was extrapolating these dotted lines at key points. One at the top, another one through reactants, and another one through products. And so this arrow over here is describing the activation energy in the reverse direction. And we can quantify that by looking at the difference of these values. And so we're going from 20 to 100, right? So 20 is where is the potential energy of the products, and 100 represents the top part of the curve. So it looks like the activation energy for the reverse reaction is going to be 80 kilojoules. And for consistency's sake, this part right here, so the enthalpy, the change in enthalpy, can be quantified by taking the difference between these two. And so that's going to be, so I'll put in negative delta H is equal to negative 20 kilojoules. Okay, so this is how much energy is going to be released from this chemical reaction. All right, so going back to the main point, we can also characterize exothermic reactions through a potential energy diagram by looking at the height of the activation energy in the forward and reverse direction. So notice that the activation energy in the reverse direction is much greater than the activation energy in the forward direction. And so that's another trend that can be observed for potential energy diagrams that describes an exothermic process. So the activation energy of the reverse reaction is going to be much greater than the activation energy in the forward direction. So once again, you guys can think about this 80 kilojoules as going from the products to the transition state. And so that height, that increase, is going to reflect 80 kilojoules, which is the activation energy in the reverse direction. All right. And so hopefully you guys kind of understand the parts to the potential energy diagram for exothermic reactions. And so we're going to go ahead and do the same for endothermic reactions. And so here, the first thing I'm going to label are my reactants. And I'm just going to go ahead and use A and B and C and D just for consistency. So here we have reactants and products. And so very similar to what I did in the previous lecture slide, I'm going to draw dotted lines at 3 key points. So I'm going to go ahead and follow this line over here. So I'm drawing this dotted line coming off from the reactants. And then I'm going to draw a dotted line coming off from the products. And then I'm going to draw a dotted line that's coming off the transition state. And so I'm going to go ahead and just mark where the transition state is, which is at the peak of this hill. And once again, I'm going to go ahead and describe this portion as the amount of energy that's invested. So here we have an investment of energy. And in another color, I'm going to go ahead and describe this as the return of energy. All right. So let's go ahead and mark some things first before we talk about delta H or enthalpy. And so if I wanted to label the activation energy in the forward direction, I'm going to be starting from the reactants, from the height of the reactants, the potential energy of the reactants, which is down here. And so I'm going to go ahead and draw an arrow from this bottom line all the way to the top part. And I'm going to label that as the activation energy in the forward direction, which reflects the investment of energy. And so I can go ahead and quantify that by looking at my values here, so negative 15 all the way to 25. And so I'm just going to think about it logically, right? So it takes 15 kilojoules to go up to 0, and then another 25 kilojoules to hit 25. So you're going to add them. And so in total, the activation energy is going to be 35 kilojoules for this specific diagram. All right, and so I want you guys to notice that when you follow this potential energy diagram past the transition state, notice that it doesn't pass the 0 line. And so the 0 line the 0 point is marked by the line from from the potential energy of the reactants. And so this dotted line is representing the 0 point, where if the potential energy diagram does hit the 0 point, then that's reflecting that all of the energy that's invested will be returned. But as you guys can see, the amount of energy that's returned doesn't hit the 0 point. So in other words, not all of the energy is returned. And so since there is a gap between these two, I'm just going to go ahead and say that not all energy is returned. That looks like an M. And so therefore, the change in enthalpy, the delta H value, is going to be positive. And so why is a sign for delta H for enthalpy positive? Well, if you guys look, the potential energy of the products is much higher than the 0 point. And so this is going to be a positive value. If the line goes below, then it's going to be a negative value. And so if you guys recall from first semester of general chemistry, if you have a positive enthalpy value, that's describing that the reaction is endothermic. And so what that means is that there's just a net gain of energy onto the system. In other words, no heat is lost to the surrounding. And so instead of heat going into the surrounding, for endothermic reactions, heat is absorbed by the system. Okay? And it's all coming from this specific point. So not all of the energy is returned. All right. And so the last thing that I want to label is the activation energy in the reverse direction. And so if I want to go from products back to reactants, the activation energy is going to reflect the energy from the products all the way up to the top of that hill where the transition state is located. And so basically I'm just looking at this area right here. And so notice that area is going to be 25 kilojoules. So the activation energy in the reverse direction is going to be 25 kilojoules. And so now that I've kind of labeled my potential energy diagram, I'm just going to go ahead and write some notes that give characteristics to endothermic reactions with respect to potential energy diagrams. All right, and so the first thing that I'm going to look at is the potential energy of reactants and potential energy of the products. And so for endothermic reactions, notice that the potential energy of the products is much larger than the potential energy of the reactants, which is kind of the reverse that we talked about for exothermic reactions. And so the potential energy of the products is much greater than the potential energy of the reactants. So that's one way to classify or characterize endothermic reactions on a potential energy diagram. Another way to characterize this is the height of the activation energy. And so notice that the activation energy of the reverse is much smaller than the height of the activation energy in the forward direction. And so the activation energy of the forward direction is going to be greater than the activation energy in the reverse. Okay? And so these are some characteristics that describes a potential energy diagram for endothermic reactions. And remember that endothermic reactions have a positive sign for enthalpy, whereas exothermic reactions have a negative sign. All right, so we're going to go ahead and just do one example, and we'll finish the lecture. So overall, we're going to sketch a potential energy diagram based on the information that the problem gives us. And so this is a one-step chemical reaction. In other words, there's only one transition state. And so if there's only one transition state, then that means that there's only one hill. If it's a two-step reaction, then that means there are two transition states. That means there are two hills. And so reading this question, it's saying that the activation energy in the forward direction is 85 kilojoules per mole. And in the reverse direction, it's 176 kilojoules per mole. So based on this information, we're just going to go ahead and sketch a potential energy diagram. And so if the activation energy in the forward direction is equal to 85 kilojoules per mole, and if the activation energy in the reverse direction is 176 kilojoules per mole, do you think that it's going to be an exothermic or endothermic reaction? And so we can go ahead and go back to our diagrams here. And so if you look at the activation energy for endothermic reactions, so notice that the forward is larger than the reverse. And in this case, the forward is smaller than the reverse. And so therefore, this cannot be an endothermic reaction, and it must be an exothermic reaction. So notice that the activation energy for the reverse is much larger than the activation energy for the forward. And so for these one-step potential energy diagrams, the activation energy for both the forward and reverse must be at the same height. They're not going to be different heights. And so for sketching a potential energy diagram, we know that PE, or potential energy, is going to be on the y-axis, and we can go ahead and write the progress of the reaction on the x-axis. So since the height of the potential energy diagram for both the activation energy in the forward and reverse direction is going to be the same, they're going to start randomly at this point. So this is just an arbitrary point. And so for the forward direction, since it's 85 kilojoules, I'm going to arbitrarily say that, hey, you know what, this height is going to represent 85 kilojoules per mole. And so since this is the forward direction. And so in pink, I'll go ahead and do the same thing for the reverse. So remember that the activation energy for both the forward and reverse must converge at the transition point. And so therefore, this height right here, I'm going to arbitrarily say that it's going to describe the activation energy for the reverse. So therefore, I'm going to put 176 kilojoules here. And so since this is a potential energy diagram, such that the potential energy of the reactants is much higher than the potential energy of the products, I'm going to go ahead and put the height arbitrarily up here, and I'm going to make sure that the top of the hill hits that top point. And so I'm trying to line this up to where that 85 kilojoule mark is located. And so I'm going to try to line this up where that 176 kilojoule mark is located. And so I'm going to go ahead and represent this as the products. If you want, you can put in C plus D, doesn't really matter, because the problem didn't really specify a specific chemical reaction. And then this is going to be A plus B, or the reactants. All right. So hopefully this exercise helps you kind of build a potential energy diagram based on the values for the activation energy. Okay. Also, I hope that this quick problem allows you to kind of exercise on how to tell whether or not the reaction is going to be an exothermic reaction or an endothermic reaction based on a specific characteristic such as activation energy. All right, so that's pretty much it for this lecture video. In the next lecture video, we'll go ahead and talk about quantifying activation energy through the Arrhenius equation. I'll see you later. Bye.